I want to introduce you to your home. This is a view of the Earth taken by Apollo 8 in 1968. It was the first photo of the entire Earth, and a photo that made a lot of people realize that the Earth has limits. It made a lot of people realize that we needed to find a way to live more sustainably on this planet with its limits. It also made us realize that this is not what a world that works looks like. This is a world that uses heat, beat, and treat, uses high temperatures, high pressures, and nasty chemicals and chemical processes. But the good news is that we do know what a world that works looks like. A world that works is locally attuned and responsive. So it uses cooperative relationships. It cultivates those cooperative relationships. Like this oxpecker and elands. The eland where it takes the insects off the eland, and the eland and the oxpecker both benefit. It's also locally attuned and responsive by using readily available materials and energy. It's not going after rare materials. It's not going after hard-to-reach energy. It's using readily available, abundant materials and energy. And it's also leveraging cyclic processes, like the tides and the seasons. It also adapts to changing conditions. And so, for example, in this meadow is able to adapt to any kind of a disturbance that comes in because it has a lot of resilience. It has multiple organisms that have overlapping functions, all of which maintain the ecosystem processes that exist on this prairie. It also incorporates self-renewal or self-healing. The organisms, nature, evolves to survive, and one way it does it is by repeating things that work, doing things that work over time, like the Fibonacci sequence or fractals. It also evolves to survive by reshuffling information. And we had Pamela was talking to us today a lot about reshuffling and also mutations, so you can integrate mistakes into what you do. Nature is also resource efficient in both the materials and in the energy it uses. So you have a beetle that uses one material, chitin, and that chitin does multiple things, has multiple purposes. It's waterproof, it's strong, it can be shaped, and it sends signals through colors like this. It's also resource efficient because it recycles or upcycles all materials. Nature integrates development with growth. So instead of just concentrating on growth, as some organisms do, nature actually takes some time and energy to develop first, so that growth can occur, and growth occurs sustainably and only to the extent the resources allow. So for this paper wasp, the paper wasp is building with modular units, repeated modular units, and it's building from the bottom up. Those are two examples of integrating development with growth. And also, self-organization is part of integrating development with growth. And life uses chemistry that is life-friendly. It uses water as a solvent, and it does chemistry in water. It breaks down materials into its benign constituents, and it uses just a subset of our periodic table. It uses mainly carbon, hydrogen, nitrogen, and oxygen, and then a handful of other elements, instead of using the entire periodic table with the kind of toxicities that come with doing that. So if life creates conditions conducive to life, shouldn't our designs do the same? We are actually a very young species. In the course of time that life has been on this earth, 3.85 billion years, we're just at the end of that time. We're very young, and we need to listen and learn from our elders. So what is biomimicry? Biomimicry is a way of looking to nature for inspiration and ideas for sustainable design. The definition we use is it's the conscious emulation of nature's genius. Conscious is purposely chosen because we go to nature with intent. We go with forethought to ask and seek inspiration, to seek sustainable ideas. How do you live on this earth without destroying life? And then we do that before we design something. Emulation means it's emulation, not copying. So we're taking those biological principles. How does a spider create silk? We're not going to farm the spider. We're not going to just create the silk and hope we get it right. We're going to look at the biological principles, and from that we extract design principles that we can hand to an architect, to a product designer, to a business organizer, to a chemist, green chemist, to emulate life. And when we say life's genius, we're talking about this 3.85 billion years of R&D that we can learn from. But what it takes is it takes us to quiet our own cleverness and to look to nature for inspiration. We have to forget what we know. So I'm going to give you 3 case studies, one on form, one on process, and one on system. The first one is form, which is how something looks, or how something, what's the morphology of this. And the story starts with glass. And we've had some talk today about glass, and the buildings, they have lots of glass. Well, the problem with glass is that birds don't see it, especially this kind of glass that's pretty popular today in some buildings that reflects basically the forest or the prairie or the lawn. That's all the bird sees. It doesn't see the glass. It says, oh, more forest. Let's go that way. And it collides. 250,000 birds a day collide and die in buildings in Europe. That's millions and millions a year. In, of course, the United States, same thing, Canada. So Arnold Glass is a company in Germany. And someone brought them an article in a magazine about spiders. And spiders, you know, they spend the night creating this beautiful web, and the last thing they need is for some bird to come foraging through the forest and crash through that web and wipe out all the work. So Arnold Glass, the president, said, well, why don't we learn from that, and let's make our windows visible to birds. So they incorporated a pattern of UV reflectant rays, which is what the spider does. The spider puts UV reflectant silk into its web. You can't see it because we can't see it, but birds can see it. And so they now have this pattern, and the windows on the right you can see. You can't see these patterns, but the important thing is the birds do, and this can save hundreds of millions of birds. The second example is an example of process. Process is how something is made or how something is done. And the work that Brent Constance, who's our next speaker, has done on biomineralization, looking at how corals take carbon dioxide and create, basically over time, limestone. That's an example of mimicking process. The example I'm giving is from John DeBerry of Caltech, who's with the Biological Propulsion Laboratory. And John has been studying how fish in schools, so a fish is swimming along, and it's waving back and forth, and it creates these little turbulences. And the turbulences actually create a push so that the next fish back in the school actually gets an energy boost. So John and his students have looked at, could you array a wind turbine farm, so that the wind turbines actually gain turbulence and energy from the turbulence of the other ones in the farm. Sorry. And so on the right here, this is a vertical axis wind turbine farm, and it has 2 benefits. One is that it takes a lot less acreage, so its on-the-ground footprint is way less than one of these larger wind turbine farms. And DeBerry, the second is that DeBerry calculates that once he and the students figure out the correct array, the correct distance and spacing, that they can get 10 times the amount of wind energy out of this farm than you could a typical wind turbine farm. So John Adel gave you an example this morning of an ecosystem approach to manufacturing or to handling of materials. This is a typical brewery, uses a lot of resources, grains, energy, water, yeast, and so on. You get some beer, and then all the rest of this on the right is waste. So for example, 10 gallons of water go in to get 1 gallon of beer, and the rest has to go out downstream or into sewage treatment plants. 45 pounds of malted barley go in to that 1 gallon of beer. 41 pounds of waste come out, which has to be dealt with. So the Wildwood Brewery in Stevensville, Montana, where I'm from, has worked with ZERI, Zero Energy Research and Initiatives, to create a closed-loop ecosystem, much like a mature forest does, in which case you have here are your same inputs and your same outputs, but these outputs all get alternate uses, very similar to the example John gave this morning. So if you want to find those biological principles so that you can mimic form, process, or system, like I just gave you in examples, there's several things you can do. One is that you can go outside. I guarantee you that if you go outside and just spend some time, we ask people to sit for 15 to 30 minutes. It takes you that long to stop thinking, to let go of what you know, and just pay attention. And when you do that, you can learn a lot about the kinds of challenges that you might be facing, because the challenges that you have done are some of the same that nature has already done. And so you can go out into nature and you can sit down and you say, well, I'm interested in lightweighting. I want to make a lightweight material. I mean, just look up at a tree. Look at a bird flying. Watch a dragonfly. These are all things in nature that have had to do the exact same thing. They've had to filter water. They've had to bring light inside of a structure, like the window plant does in the desert. So we can learn from nature. A second thing you can do is bring a biologist to your design table, someone like me who's a biologist but has also been trained in biomimicry. And a third resource is what I'm going to talk about for the rest of my talk, which is Ask Nature. It's an online catalog or library of nature strategies. So this is going to be a little tour of Ask Nature. But this is what we were thinking at the beginning. Ask Nature is where biology and design cross-pollinate so bio-inspired breakthroughs can occur. And it's an online meeting place for people from different disciplines to get together and maybe talk about biomimetic design and sustainable design. So biomimicry can be used as an inspiration for whether you want to go from biology to design, you just want to look for some cool strategies that you could apply to some design as yet unnamed. Or it can be for challenge to biology. You've got a challenge in mind. Where can I find an answer? You don't have to read this. I'll go to a close-up in a second. But I wanted to show you what we call the biomimicry taxonomy. And this is how all of our biology in Ask Nature is organized. It's organized by function. It's organized by what it is you want to do. So the important part about biomimicry, and that we have to spend some time teaching people, is just plain to figure out what it is you really do want to do. Because you may think you know what you want to do, but that might not be what you want to do. So we have 8 groups, 30 subgroups, 162 functions. And this is the bottom half. And the idea here is that this is something you could print out, but eventually we hope to have it work better online itself. And you might say, well, I want to learn how to capture liquids. Or I want to sense chemicals. So that's the strategy. That is what you really want to do. And then you go to Ask Nature. And instead of jumping right to that big green search box that everybody jumps to, instead, you want to browse. And when you click on Browse, you get this Try Browse. Don't memorize this. It's all going to change next year. So you say, okay, I want to get and store or distribute resources. I actually want to distribute energy. Oh, here's an interesting one. This is about the toucan. You get a little preview and you say, okay, I'll take a look at that one. And you get this strategy page with a headline and hopefully a really beautiful photo, or a photo that maybe even teaches you a little bit about the strategy. Scroll on down on the strategy page and you get the most important sentence that you've never noticed on a website. And this is the bill, which is the part of the organism, of the toucan, the organism. What does it do? It acts as the heat exchanger to regulate body temperature. How does it do it? What's the biological strategy that you can make into a design principle? It does it by adjusting blood flow. And if you dig deeper into the literature or into the next section I'll show you, we try to give you a little more information about what that biological principle does. We give some application ideas and HVAC systems, for example. And then there's a piece of the biomimicry taxonomy. You can, if you didn't like that strategy, you can click on one of those other ones and get some other strategies to look at. Then we always have a scientific excerpt. Here we've thrown in a video, and this is one of the ones where we have an artist who has actually diagrammed, illustrated the biological principle, and we're starting to put in more of that design principle I talked about. We also have case studies on Ask Nature, so we have 161 case studies or product pages where you can learn a little bit about another existing biomimetic design. So this is where we are. We launched in 2008 with 600 strategies, just a couple dozen case studies. Now we have over 1,500 strategies on Ask Nature. We have 161 case study pages, and we have coming 120 of nature's chemistry strategies and 20 of nature's, actually more than that, I think we have 35 of nature's chemistry case studies, because we're really interested in nature's chemistry, that whole life-friendly chemistry. So this is just a peek at what's coming up next. With Ask Nature, 2013 is going to be a whole new design. Sleek and elegant toolkit with easily digestible, that's one of our problems, digestible, discipline-oriented, nature-based strategies. It'll behave like an ecosystem, it'll create those symbiotic cooperative relationships, and it will reward its members for working together. So, we are part of nature. We're not separate. We share this planet with 30+ million species. They are our example of a world that works. And we need to open our eyes, learn from them, and pay attention. Thank you.